Hi guys, Audrey here. So today we're going to do a video on the comparison test. This is part one of a three-part video series of when the comparison test goes crazy. So we're just going to see some challenging examples of using the comparison test. Here we have the sum n equals 1 to infinity of n ln n over n plus 6 cubed. Well, the first thing we notice is that the denominator is growing faster than the numerator, so definitely our test for divergence will fail. You can actually do the limit and check that if you would like. So then the next thing we see is this kind of looks P-series-esque. It's got n to the powers, it doesn't have a factorial, it doesn't have an exponential, so the ratio test is kind of out. So really we're going to be trying to do a comparison test. We also have that ln n there. Now a lot of times ln n tells us try an integral test, but in this case, if I were to replace all those n's with x's, that does not look like a simple integral to do. So really this leaves us with the comparison test. Now we've learned techniques for picking a series to compare to. One of those techniques is to just take the big stuff. So that's what we're going to do here. We're going to pick a series for comparison. And we're going to do that by taking the big stuff. Well, on the top, my big thing is n ln n, and on the bottom, my big thing is n over n cubed. So this would give me then n ln n over n cubed, which gives me ln n over n squared. Okay, so we want to compare to the sum n is equal to 1 to infinity of ln n over n squared. Now, when you're looking at that ln n over n squared, you might think, hey, that ln n's not so great. Let's pick something else to compare to. Let's get rid of that ln n. And that might lead you to try to bound ln n by giving you ln n is less than n, a thing we know, which would tell us that ln n over n squared is less than n over n squared, which would be 1 over n. Well, we know that the series 1 over n is the harmonic series, and that series diverges. So the inequality we would want would be a greater than there. So already we can kind of see the inequality fails for the comparison test. So then we might try the limit comparison test with this, and it turns out that the limit comparison test would also fail. So getting rid of the ln in that way actually doesn't work here. Now, if you actually have to go through and do all of that work to see that, that's fine, as long as you then come back and say, okay, well, now what else would I pick? So comparison and limit comparison both fail with n equals 1 to infinity of 1 over n. Now, the limit comparison will almost always fail when we have a ln n involved, if we don't have a way to get rid of that ln n, because ln n is going to infinity as n goes to infinity, and so oftentimes we'll have a 0 or an infinity as our result. Okay, so that said, you might go back and be like, so here we're like, pick something else. Pick something else. So you might go back and be like, well, the comparison failed there, so maybe I could just compare to 1 over n squared, I mean. So what about comparing to the sum of 1 over n squared? Well, it turns out that that is going to fail as well. So we know that 1 over n squared, the series is a p-series. P equals 2, which is bigger than 1, so it's a p-series that converges. So this converges. So what we would want is ln n over n squared to be less than 1 over n squared. But I can see ln n is definitely not less than 1. Ln n is growing. 1 is just kind of staying the same. So that inequality fails for us. And again, for the same reason that the limit comparison test failed with 1 over n, the limit comparison test will fail here as well. So we have both comparison and limit comparison test fail. Okay, so basically what that means is 1 over n squared don't work. Again, totally reasonable if you think about those as series that you want to compare to. But once you've seen that they both fail, we're then going to go back up and be like, okay, so we tried to pick a p-series, but that p-series didn't work. So what would happen if we leave the ln n on top? Well, now this looks like something that is much more reasonable to think about for the integral test. So we're going to actually have to go through and figure out, does this thing converge or diverge? And we're going to use the integral test. If you go back and watch the video where I talked about the comparison test versus the integral test, hopefully you'll see that we need an integral test for this thing. A comparison test won't work. If that were n cubed, however, a comparison test would work. So we're going to try the integral test. So for my integral test, is it positive? Yes. Is it continuous? Well, there are no negative n values, and n equals 0 is not a possibility here. So yes, it is continuous on the interval. Is it decreasing? And the answer here again is yes. So we can see that because we can see that ln n grows more slowly than n squared. So the denominator is getting bigger faster than the numerator. So it seems like this would be decreasing. But we can also just really quickly check the derivative just to be safe. So we're going to check the derivative. So ln x over x squared prime, it gives me the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. And I want to know, is this thing less than 0? The x to the fourth on the bottom doesn't matter. So basically I'm saying 1 over x times x squared, that's x, is x minus 2x ln x less than 0. In other words, is x times 1 minus ln x less than 0. Our x, we're thinking of it as if we are starting at 1. So x itself is always positive. So then what that's the same thing as saying is 1 minus ln x less than 0. And that would give me 1 is less than ln x. In other words, ln x is bigger than 1. And yes, that happens for x bigger than e. So as long as our n value is bigger than e, this thing is decreasing. Okay, so we can apply the integral test. So let's do it. So we want our integral test. So we're checking out the integral of ln x over x squared dx from 1 to infinity. Oops, we're applying the integral test. So we're going to start off by rewriting this as a limit. T approaches infinity. 1 to t ln x over x squared dx. Now this is going to be an integration by parts here. So we're going to pick our u and we're going to pick our dv. Now we can use Liet, our mnemonic device, for this to see that our u is going to be ln x. Actually, we'll do that in green. Our u is going to be ln x. Our dv will be x to the negative 2. So that's 1 over x, negative x to the negative 1. And we get negative ln x over x plus the integral of 1 over x squared dx, which gives me negative ln x over x minus 1 over x plus c. Okay, so let's go back up there. Now we're going to put this back with our limit. Limit is t approaches infinity, negative ln x over x minus 1 over x. That I'm evaluating between 1 and t. Now remember, first we plug in the bounds, then we evaluate the limit. So limit as t approaches infinity, negative ln t over t minus 1 over t, plus ln 1, that's just 0 over 1. So 0 over 1 is just 0, plus 1 over 1, so that's plus 1. Now, when I plug in my infinity here, that right there is going to 0. And ln t over t, well, the t is growing more quickly than the ln. So ln t over t is also going to 0. And this limit, therefore, just equals to 1. Okay, so what that tells me is that the integral from 1 to infinity of ln x over x squared dx converges, which means that the series as well, the sum n equals 1 to infinity of ln n over n squared also converges by the integral test. Let's remember what we were doing here, because this was not our original problem. So first we said, I have n ln n over n plus 6 cubed, and I'm going to do a comparison test. I forgot to write fails by the test for divergence. Test for divergence fails. Not bad. Okay, so we want to do a comparison test. So let's pick a series for comparison. We did this by taking the big stuff, looking at what was dominant in the numerator and denominator. Then we said, typically we want to compare to a p-series or a geometric series. The thing that we got was neither of those things. So we said, well, what p-series or geometric series could we kind of get from the thing we got? And it turned out that both of them ended up with the comparison test and the limit comparison test failing. When we tried the harmonic series and when we tried the p-series 1 over n squared, comparison and limit comparison both failed. So we said, okay, I guess we're gonna have to figure out if this ln n over n squared converges or diverges. Ah, that looks like a reasonable thing for the integral test. So we applied our integral test here and we were like, the series that we picked for comparison converges. So now we want the original thing to be less than it. So what we want here is for n ln n over n plus 6 cubed to be less than ln n over n squared. Okay, is this true? Well, it looks true, or at least hopefully it looks true to you, but we're still going to do some cross multiplication just to make it really clear that it's true. So I'm going to multiply the n squared over, so I'll have n cubed ln n. Is that less than, so is this true, question mark? Is this less than n plus 6 cubed ln n, question mark? Well, now hopefully it's even more obvious that it's true, because we can cancel those n's out, and yes, for positive n values, n cubed is less than n plus 6 cubed. So this is definitely true for positive n values. Okay, so we're actually done. Now I can say then that the sum n equals 1 to infinity n ln n over n plus 6 cubed converges by comparison to the sum n equals 1 to infinity ln n over n squared, which converges by the integral test. So in other words, inside of our comparison test, we had to do an integral test. And that's all. Hopefully that helped you guys to think about comparison in a more broad way. All right, that's all. Bye, guys.